the Daniel K. Inouye telescope in Hawaii. And this is a picture of the surface of the sun. So you can see the boiling cells coming up, and then the dark lanes where the matter flows back down. For size, each of these cells is about twice the size of Africa. If you look at pictures on the web, they will often compare things to the size of Texas. Texas is half as big as South Africa. So that's what the surface of the sun looks like in visible light. And the magnetic field that is working its way to the surface sometimes floats to the surface in tightly organized regions, which we call active regions, because they're regions of activity. Astronomers are very clever about their names. And you can see that sometimes it appears to just appear instantly. That makes a challenge for predicting exactly when something is going to appear, right? If you watch in the center of the sun, suddenly there will be an image right there. It just appeared out of nowhere. So this is what we think is going on. The upper left is a picture of the sun. You can see these big arch structures. That is the magnetic field with glowing plasma stuck inside of it. The picture of the magnetic field is there in the diagram. And in the center, there's a movie from NASA that shows what we believe is happening. The magnetic field branches up through the surface and sometimes can get a little twisted and release a burst of energy as well as a blob of plasma. So here it is coming through the surface. And now looks a lot like the picture on the left. And then you can get another blob that pinches off, suddenly bright, and so on. So that brightening we call a solar flare, and the part that was ejected from the sun we call a coronal mass ejection. And sometimes there are very intense bursts of energy on the sun, and it's difficult to synchronize the cat sneeze with the explosion, but there, we got it pretty good. So these bursts of energy are what we study in space weather, right? Those affect the Earth, and I'll describe how that happens shortly. Here's a movie, if we can get it to play, of the sun in extreme ultraviolet, so a very short wavelength, and you can see the loops and so on, and you can see many little bursts of energy coming off. So that's many different flares. And let me point out the size of the Earth here. So these events, the big arches of magnetic field and the explosions, are much larger than the Earth. Sometimes, get that one to go, these bursts send big blobs of charged particles and magnetic field out into the solar system. That might hit the Earth. If it does hit the Earth, then we get a space weather event. So sorry for the somewhat vulgar explosion of material. So those were pictures of the surface of the sun. If we kind of zoom out a little bit, we can take a picture with something called a coronagraph. So the white circle there is the image of the disk of the sun. So you need to block that out so that we can see these other features, which are about 1 million times dimmer. But it's essentially light from the sun that is scattering off of the material being ejected by the sun. So the more dense it is, the brighter it appears. So some of the features, like the one sort of, if you think of it as a clock, kind of at 1 o'clock and so on, that is kind of steady. That's the solar wind coming out. And then you can also see explosions, like in the bottom part and then in the upper left there. So we now see that there's material coming out of the sun, but we don't really have any perspective. We don't have any depth perception here in space at all. It could be going towards us or slightly away from us or whatever. So we need to use more information to try and predict whether or not that's going to hit the Earth. The sun, isn't continually popping off flares and so on. It has, you could think of it as like seasons, sometimes there's summer and winter, there's more storms in one season or another. The sun's season lasts, 11 years. And during some times, there's many more flares, solar maximum activity. And then there are times when the activity is much lower at solar minimum, meaning the minimum level of activity. So what happens when there's a storm? I mean, you look at this and you think like, that almost looks like a tornado. But there's also all of these little sparkles on there. Those are very tiny flares, which individually they're small, but maybe they add up to a lot of energy, and so on. So I'll show you a short video that kind of, talks about many of these things. I can get it to play and hopefully you can hear it. So this is a video made by SANSA.
The advancement of space-based technology has brought about many benefits to our society. It helps us to communicate, to find our way, and to predict adverse weather conditions. It even helps us to plan our cities and towns. So what would happen if all our satellites stop working? It's unlikely that all our space-based technology will go out all at once. But a big space weather event could damage our satellites and ground infrastructure and cause issues with daily tasks. We rely on satellites for air traffic communications and weather prediction. We rely on satellites for navigation. Power grids are vulnerable to the onslaught of continuous space weather events. Modern farming methods are increasingly reliant on space-based technology for sowing, crop care, and harvesting support. We rely on satellites to provide time synchronization that allow for international money transfers and ATM banking. Space-based technologies are a catalyst for development, innovation, and creating a better life for all on this earth. It is thus important to protect these technologies against threats such as space weather, which can harm technology and impact our daily lives. At the South African National Space Agency, we work around the clock to create products and services that will help mitigate the effects of space weather to our technologies to secure a better future for South Africans and the continent.
All right, so hopefully you enjoyed that short video that gave you a lot of things that can happen during space weather. And many of these are captured on this diagram, which are the effects of space weather. So in the upper right, there's the sun, of course, that is the source of all the space weather. And then the next row is, of course, out in orbit around the Earth, where there are spacecraft, astronauts, and so on. When there's more activity on the sun, it puffs up the atmosphere and there's more friction on the spacecraft, so it affects their orbits. The charged particles coming from storms can affect astronauts. Then the next layer is what we call the ionosphere. So it's the part of the atmosphere that is ionized by the ultraviolet radiation from the sun. So instead of being neutral atoms like we breathe here on the ground, a certain fraction of the upper atmosphere is turned into positively charged ions and free electrons. We monitor the total electron content, meaning how many free electrons are there in the atmosphere every day, to understand how radio signals will propagate through the ionosphere and get reflected and so on. I'll have another diagram about that later. We affect aircraft. There can be radiation hazards for crew and so on. We talked about the power grid. So there can be what we call a geomagnetically induced current, or GIC. It's a complicated way of just saying when the magnetic field changes, it can make an electric field. So it can make electric currents. Now that could overpower the transformers on the power grid. It can produce electric currents in pipelines, like oil pipelines or something, that can cause extra corrosion in the pipeline. There can be disruptions in cellular signals. And so my favorite part, of course, is the, measuring your position on the Earth using GPS. And in this diagram, you'll see that they have navigation errors pointed to a locomotive, a train. Of course, trains don't use GPS to figure out where to go. They just follow the tracks. But there are other times when a vehicle needs to use GPS to know its location. Like for instance, in this photograph of a narrow mountain road in foggy conditions and so on, this vehicle is clearing the snow off the road to make it safe for others. But he may or may not be able to see where the road is. So I've been told that the snowplow drivers will have several sensors and maybe a little vibrating part of the seat that says, oh, you're going too far to the left, or part of that goes to the right. So we don't know if that's true or not. So many parts of the world really do need precision GPS at all times. And if there's a solar storm at the same time there is a snowstorm, that could cause a problem. So you want to know about that ahead of time. All right, and then I'll talk a little bit about satellite drag. So last year, I guess I'll point out that there are several satellites in orbit. So here's an animation which shows most of the satellites around our Earth. There's this outer ring, which are the geostationary satellites. Those are the ones that broadcast television signals and so on. They rotate around the Earth at the same speed that the Earth rotates, so it takes 24 hours to go around. So it stays in the same spot of the sky. There are also many of these, angry bees right above the surface of the Earth. When you think satellites are in orbit, you think, wow, they're really far away, but you realize they're only like 500 kilometers above the surface. So they're not that far above the surface, and hopefully none of them crash into each other. But all of them are experiencing some friction with the atmosphere, which we call satellite drag. So their orbits do slowly change. We need to keep track of them. Military satellites need to avoid crashing into other satellites and so on. So as the sun is more active, it increases the amount of drag on the satellites. And last year, there was a case where SpaceX, which is launching thousands and thousands of little satellites into orbit to be a worldwide internet connection. They launched 47 satellites at once, and their method was to launch the satellites into a lower orbit of only a few hundred kilometers and turn them on to see that they work, and then they would individually be boosted out to their final orbits. Well, during this time when they're in the staging area, there was a geomagnetic storm that increased the density of the atmosphere at 200 kilometers enough to cause 40 of the 47 satellites to crash back into the Earth. So if you think of the cost of each satellite, between a quarter of $250,000 and $500,000, plus another $20 million to launch them. So those are dollars, not even rands. That space weather event cost SpaceX probably about $50 million, just because they didn't necessarily consult the right space weather forecasts. There was a warning from SANSA about the chance of a geomagnetic storm the next day. And I believe that SpaceX is now very interested in getting space weather reports before they launch. All right, so what's one of the things that can happen? So this is an animation from a model of the upper atmosphere that shows what happens when the sun, let's see, it is going, it goes kind of slow because it's like a frame every minute of clock time. And this illuminated area is the part right under the sun, right before there's a flare. You can see that it's starting to grow as the sun's X-rays become brighter and brighter. And the different colors indicate what radio frequencies are absorbed by the atmosphere instead of being reflected. So if you're trying to communicate using that frequency, over India right now, for instance, you would suddenly lose contact with the airplanes that you're trying to talk to. So you might need to change frequency, which means the airplane has to also know to change frequency. So this sort of map is present in every air traffic controller station, and airplanes now, by rule, have to include space weather predictions in their flight plans. So this is one of the areas where daily measurements from space weather are important. Okay, so remember with the coronagraph image, I mentioned that you don't really have much depth perception of where is that blob going. So on the right is a mathematical model trying to include where on the sun the eruption comes from and where it's traveling in space. You'll see the kind of spiral pattern. That's because the sun is rotating, right? And so those of you as kids, you're outside with the garden hose and, the water is coming out straight from the hose. But if you turn and spin around, right, the water looks like it's making a spiral pattern. So the same thing happens with the wind from the sun. So on the diagrams, one is the density of the solar wind and the other one is the speed. And so this was just last week, right? And the 29th of July, the same time period that is shown in the coronagraph image. And you can see when there's a blob out of the coronagraph, you can now see that there's a blob coming towards the Earth over here. So this is the Earth. Stereo A and stereo B are some satellites that are used to measure the solar wind. And you can see that the blob is coming towards us, and the model predicts that, between the first and the second, we would have an increase in density and speed, mostly the density there. And you can see it's coming towards us, it's coming towards us. If it had come off at a slightly different angle, it may have missed the Earth entirely. And that's one of the things that space weather forecasters are trained to do, is to estimate when such a blob will hit the Earth, if it hits the Earth at all, right? It could miss it, or maybe just a little glancing blow, or it could be a big event that causes a geomagnetic storm. All right, so that moves on. All right, so SANSA is one of several space weather centers around the world. We are what's known as a regional center. There are others that sort of try to be global centers. Of course, there's in the US and the UK, and then Russia and China kind of alternate being a space weather center. There are three main things that we try and predict about space weather. The first one are the radio blackouts. So this is the X-rays from the sun that ionize the upper atmosphere, preventing storms from going. So just like for terrestrial weather, when there's a hurricane or cyclone coming, we try and predict how strong it's going to be. How important is it? And so there's a scale from 1 to 5. So minor, strong, finally to extreme. And this describes the sorts of things you might happen with an extreme storm and so on. And then also prediction, statistically, how often do these happen? So these extreme storms, maybe we get once per decade. Less extreme ones, maybe we get one per year, or they won't be one each year. During solar maximum there will be several, and then during solar minimum hardly any at all. So there's radio blackouts. The second kind is a solar radiation storm, or an S-type storm. And again, they go from S1 to S5, and we get many tiny ones and hardly any super extreme ones. And the third kind, of course, are the geomagnetic storms, or the G storms. So this is a change in the Earth's magnetic field, which changes navigation and aircraft and so on. So those are also very important. The extreme storms actually are more common. We might get 4 per cycle instead of just 1. So every day, SANSA will issue warnings about the conditions for all 3 of these hazards. All right, I guess we'll have lots of time for questions, because we're already on to the summary. And so this is the quiz time. I'll show another video, and if anybody sees things that they don't think were mentioned before or aren't mentioned correctly, then you can ask about that in the questions section. So here we go.
Why is it important? What is the threat? What is the impact on technology? How does it differ from terrestrial weather? What is space weather? The Earth, our home, orbits our life-giving star called the Sun. The Sun is not only extremely hot, with a surface temperature of about 6,000 degrees Celsius, but it also has certain activities happening on its surface, like solar flares, coronal mass ejections, storms, and heat, basically emitting millions of particles, radiation, and energy into space. This causes space weather. And even though the Sun is about 150 million kilometers away from Earth, our planet can still be affected by space weather. Just like Earth's weather has seasons, space weather has seasons too. The Sun has a cycle of about 11 years, known as solar minimum, with low solar activity, and solar maximum with high solar activity. But even during times of low solar activity, solar storms and solar flares may occur. Solar flares are giant explosions on the surface of the Sun that occur when twisted magnetic field lines suddenly snap and release massive amounts of electromagnetic energy. A solar flare takes about 8 minutes to reach Earth and travels at the speed of light. Charged particles from solar storms can reach the Earth in a mere 20 minutes, while coronal mass ejections, which is a large cloud of charged particles, will take 1 to 4 days to reach the Earth. When the magnetic field of a coronal mass ejection interacts with the Earth's magnetic field, it causes a temporary disturbance known as a geomagnetic storm. Space weather is constantly interacting with our Earth's magnetic field, but the impact of a space weather storm will not harm humans and other life forms on Earth, as we are protected by the Earth's magnetic field. The Earth is a giant magnet, and the field it generates acts like a shield against solar particles and radiation. However, our astronauts, the aviation sector, and satellites are at risk. If satellites are hit by space weather, radio communications, telecommunications, navigation, and weather services may be affected, and many more electronics can suffer hardware errors and failures. This can disturb internet connectivity, have an effect on your cell phone, interrupt satellite TV, and even cause radio blackouts. In severe cases, the power grid may be damaged. Astronauts also have to be aware of space weather and should avoid spacewalks during space weather events in order to avoid the radiation from the Sun. Passengers and crew on long-haul flights can also be exposed to radiation during space weather events, which is why the International Civil Aviation Organization recommends that space weather information be included into flight plans. But the effects of space weather interacting with our magnetic field can also be spectacular. The magical lights in the sky, called aurora, are an effect of space weather storms such as solar wind, solar energetic particles, and coronal mass ejections. And while we enjoy the beautiful views from our balconies, looking up into the sky, we can remember that our magnetic field is working non-stop to keep our planet safe. Scientists from around the world are constantly monitoring the Sun and our magnetic field to predict space weather and warn of their effects. The South African National Space Agency is expanding to do this on a 24/7 basis and offers several products and services to mitigate the effects that space weather may have.
All right. So hopefully everybody enjoyed that and learned a little bit about the sun and how storms from the sun can affect various aspects of technology here on Earth. And I'm happy to answer questions. Thank you.
Thank you. Thank you very much, Dr. Snow, for the talk. It was really great. There's about 3 questions that are currently here. I'll just read the first one. The first one is from Mr. Kajan Laken. It's thank you, Dr. Snow and SANSA. The James Webb Space Telescope uses infrared wavelength. What wavelength is used for our sun measurements? Thank you. That's the first question. Must I read all, or are you just going to answer that one?
Yeah, let me answer that one first. So yes, you're talking about the new James Webb Space Telescope. So it is looking primarily in the infrared at distant stars and so on. So of course, we actually do measure the sun's brightness in all wavelengths, including infrared. But most of the images that I showed were from ultraviolet and extreme ultraviolet. So the infrared radiation from the sun comes from the deep in the surface, kind of under the visible light surface, and it's very stable. It changes very little. The magnetic storms occur above the surface in what we call the chromosphere or the corona. That's where the gas is very hot and it's lower density, so the plasma is confined to the magnetic field. So when the magnetic field gets twisted and reconnects, releasing energy, it's from the areas where the ultraviolet light is coming from. So that's why I showed all ultraviolet and extreme ultraviolet images instead of infrared. On the sun, since it's a normal mellow star, the infrared light changes very little over the solar cycle. The ultraviolet will change by a factor of 10 or 100, whereas the infrared changes by a tiny fraction of a percent over the solar cycle. So it's very stable. So that isn't really what produces the space weather events.
Thank you, Dr. Snow. The second question is from Laken again. Does our sun cause gravity?
So maybe I changed the wording just a little bit. So gravity, right? All mass in the universe produces has a gravity field, and the sun. The particles that form together to make the sun all together produce a big gravitational field. The force of gravity is what causes the fusion in the core, and the gravity from all of the material in the sun is what keeps the planets in orbit around it. So the sun is big. It's 99% of all the mass in the solar system. All of the planets together only are like 1% the amount of mass as in the sun. So yes, the sun's gravity field extends throughout the solar system, and that's what keeps the planets orbiting nearby.
Thank you, Dr. Snow. The next question is from Johan Pretorius. Like weather apps, are there any apps for space weather?
Are there any what of space weather?
Apps for space weather, just like your terrestrial weather apps.
Oh, yes, there are some apps. I think NOAA produces an app. Some other apps used to exist, but seem to have stopped working. There's one that predicts when the aurora will appear. Those are an effective space weather, and it's called Aurorasaurus. Right, it looks like a dinosaur. So yes, I think if you search for space weather apps, you will find several.
Thank you, Dr. Snow. We move on. The next question is from Elizabeth. How long to solar minimum and maximum seasons last? How long to solar minimum and maximum season last? I know you mentioned 11 years. Is that for each season or for both combined?
So the 11 years is both combined. So from one minimum to the next minimum is about 11 years. It's not exactly 11 years. It varies between 9 years and 13 years. And then so solar maximum is usually somewhere in between there. So from the last minimum, which was in at the end of 2019, till now, we are in the increasing part of solar activity. We'll probably reach the maximum within another few years. And then there will be a slow decline back to minimum. I'm saying, about 2 years and so on, because we still don't quite understand the solar cycle well enough to really predict exactly how long it will be or exactly how big it will be. The consensus of all of the different methods of predicting it say that this one, which is called solar cycle 25, we started measuring them hundreds of years ago and started numbering them, and it will be bigger than the last solar cycle, but probably not one of the largest ever. But the maximum will be within the next few years, and then the next minimum should be around 2030 or so. Yeah, who knows?
Thank you, Dr. Snow. A follow-up question from Elizabeth. How does the solar weather affect our own terrestrial weather on?
So the terrestrial weather is caused by sort of different processes than solar weather, space weather. So space weather are, eruptions on the sun that produce the showers of particles and so on. Whereas terrestrial weather is, differences in heating over land and water and wind and so on. So space weather is not directly related to terrestrial weather, but so yes, that's where we say yes, it affects our technology, but it doesn't make it rain.
Okay. Another question. I think this one is directly to you. I want to take on a project that studies the sun for my master's with SANSA, as I'm already funded by them. Is it possible to work with Dr. Snow for my master's research to study the sun?
Yes, quite possibly. You can send me an email at, I can show on the next slide. There's my email, msnow@sansa.org.za. And you may have already sent me an email. I don't know the name right off the bat. But yeah, we can talk about doing a master's project. That sounds great.
Thank you. The next question is from Pierre Silias. How do we know how long it takes for particles to travel from the center of the sun to its surface?
That is a good question. So, we can make models of the density in the sun from the surface to the core. We know the rate of production because some of the processes in the nuclear reactions produce neutrinos, which interact with matter very lightly, so they get here quickly, and we know the rate of energy being produced. And then, it's essentially a random walk through a very dense forest for those photons. And the numbers I've heard quoted are thousands of years to many thousands of years. But I'm not an expert in those models.
Okay, thanks, Dr. Snow. The following one is from Abdelmoyamen Nosir. Hopefully, I'm pronouncing that one right. What are the techniques and parameters that are used in calculating and determining CMEs and flares?
So I'll do the flares first. So that essentially they're characterized by how by the maximum level of X-rays in the soft X-ray band. And so we classify those based on, is it 10 to the -4 watts per square meter, 10 to the -3 watts per square meter. So that determines whether it's what we call a moderate flare or an extreme flare. And so that's easily measured from some satellites in orbit, mostly the GOES satellites. And the CMEs are a little bit trickier to measure. You can see them in the coronagraph image and kind of estimate the speed, but that depends on the angle, right? That you see it coming out from the sun at a certain rate of, degrees per hour. But depending on the angle, maybe that translates into 1,000 kilometers per second or 2,000. And that will go into the calculation of when it will hit the Earth. You can measure its density by how bright the scattered light is. So you can measure that. The big key that is extremely difficult to know is the direction of the magnetic field, right? So when it's difficult to do a remote measurement of the strength and direction of a magnetic field, there is a new mission being developed called PUNCH, which will use the polarization in several angles. And I'm not an expert on quantum mechanics, but in theory, that you can measure the strength and direction of the magnetic field based on the polarization of light. That will really help understanding the configuration of the magnetic field in the blob that may be hitting the Earth. If the Earth's magnetic field is pointed this way and the magnetic field of the CME is the same way, they sort of just slide past each other. If they're oppositely directed, then when they touch, there could be reconnection, and that will trigger a larger storm. So that's an advancement that is on the horizon, but hasn't launched yet. Now you sort of have to look at where did it come from on the sun, trying to do some estimate of whether it's northward pointed or southward, and we go with that.
Thank you very much. The next one is from Siv. Hi, Prof. Snow. Thanks to you and SANSA for this informative webinar. Has SANSA started incorporating the use of artificial intelligence? And if yes, which function is it currently performing?
So I think instead of calling it artificial intelligence, we use what we call machine learning. So it looks at all of the past events and finds correlations between them. So if there's a clue in the data, then the machine learning algorithm will point that out and say, oh, we're now in the situation like we saw in the past. And that gives us more information about what the storm is likely to be, and we can send out bulletins and warnings about that. So I think that's mostly the use for machine learning or artificial intelligence right now.
Thank you very much, Dr. Snow. Next question is from Pierre Cilius. When is it predicted that the next solar maximum will occur?
When is it predicted?
That the next solar maximum will occur.
Okay. I believe that the consensus is that the solar maximum will be in 2 years, although the measurements of, say, the sunspot area and numbers is ahead of earlier predictions. So it may be that the solar maximum is earlier than the consensus. There's many different ways to predict it, and some of them work better than others. One of the key factors is just measuring the strength of the polar magnetic field, right? The magnetic field drifts towards the poles before being subducted back down to the base of the convection zone, and so on. And I don't want to bore everybody with too much math and so on, but there's a lot of uncertainty in that prediction. So we'll just say within the next couple of years.
Thank you very much. Next one is from Litlotlo. Can coronal mass ejections be deadly for people on Earth, or is it mainly astronauts that are in particular danger?
Yeah, so it's not a health hazard for people on the Earth. The coronal mass ejection is probably also not the hazard for astronauts. It's the high energy particles. So when there's a solar flare, right, you get high energy photons, particles of light, which are X-rays. And then there are also very high speed particles moving at almost the speed of light. So it's those particles are what we call radiation. And that can be a health hazard for astronauts up in space, and to a certain extent also aircraft at high altitude. I think it's not necessarily a health concern for people on the ground, because the atmosphere and the magnetic field are protecting us from those events at the surface.
Thank you very much. There's just two more questions, and then hopefully we're done. Can space weather affect mobile phones?
Yes.
Affect mobile phones, sorry.
Yes, certainly. You saw that in at least one of the videos. One way is that you're communicating with the satellites for location information, and the cell phone signals may also be reflected off the ionosphere, and so disruptions in that may cause a loss of signal. So your phone signal may become unstable. Maybe during a phone call, there will be static, or maybe the call will be dropped, or that you're having trouble connecting to the internet. So yes, it can briefly cause disruptions in your connection. It probably won't damage the hardware of your phone. So as soon as the space weather event is over, your phone will be back to working order. But yes, it can definitely disrupt the signals.
Thank you very much, Dr. Snow. And we have one last question from Mr. Kajan Lakan. A magnitude M3 earthquake releases 3 billion joules of energy. About how much of energy does a space weather event release?
That's a good question, and I don't have the answer. Yeah, that's interesting. Is it more or less energy than in an earthquake or a hurricane or something? Because it's affecting the atmosphere at the edge of space, which is lower density, so it doesn't take as much power to cause a big disruption in it. Yeah, I'm not gonna try and guess, because if I say a number, it could be wrong by many thousands. So the answer is yeah, I don't know, and that's an interesting thing to think about. Thank you.
Thank you very much, Dr. Small. I think that was the last question. I'm not sure if any of the audience still have more questions to ask Dr. Snow. We have about 10 minutes left on our time to 2 o'clock. I'm just going to give it 10 seconds to see if there are any more questions. And then if there are no more questions, and then I'll close. I'll just give it 10 more seconds. Johan Pretorius is saying thank you very much.
Well, of course. Thank you for having me.
There's just one more questions that came up.
Okay.
Can cats sense space weather?
Oh,
That is
you
from
noticed that.
P.S. Elias.
You noticed that cat. Well, that's an interesting question about animals and space weather. And in fact, the answer is yes. So maybe not cats, but certainly many other animals, including birds, when they are migrating, they're navigating using the Earth's magnetic field. So during a space weather event, the Earth's magnetic field is modified. It might change direction slightly and so on. So migrating birds can get lost. And, one of the classic examples is, of course, that people raise homing pigeons, right? They raise pigeons to run races and you release them and they fly back home, and you don't want these birds to get lost. So one of the customers for space weather are the pigeon racers. And I'd always heard this. And then a few months ago, someone actually called me to ask about that, because he had pigeons and he wanted to know the forecast for the next day. So these pigeons they can be very expensive. So you think, well, we've lost $30 million worth of satellites. Yeah, but that's from a big corporation. If you're someone who just has some birds, they're precious to you as well. So yes, animals can indeed be affected by space weather if they're using the magnetic field to navigate. And so then indirectly, it can affect cats because maybe those pigeons that normally don't come over your house suddenly are perching on your wall, and your cat can interact with those birds. So yes.
Thank you, Dr. Snow. Two more questions that just came up from Aisham Kize. How do the sun rays make the aurora borealis on planets?
Sure. So the aurora are caused by charged particles hitting molecules in the atmosphere and adding energy to them, which excites an electron to a higher state. And then when that electron decays back down to the rest state, it releases light. Okay, so the lights that we see from the aurora are the energy produced by charged particles hitting those molecules. The charged particles are normally deflected by the Earth's magnetic field. And so even though there's a continual stream of particles from the sun, we don't have aurora, strong aurora every day. So some of the charged particles can sneak in through what's called the cusp region between where the magnetic field is going in and out, but it mostly appears at the poles of the Earth. During one of those geomagnetic storms, you can cause the Earth's magnetic field to have a break in it, where the magnetic field reconnects, and that allows more particles in. And in one of the animations, you saw that break and the particles went down the tail of the magnetosphere and then came back and hit the Earth. So that's what's producing the aurora. So the geomagnetic storms will produce more aurora because they open up holes in the magnetosphere to allow those charged particles to hit the atmosphere.
Thank you, Dr. Snow. One last question from Siv. Does SANSA also monitor the impact of space weather on other planets like Mars?
SANSA doesn't necessarily issue warnings about space weather on other planets, but there are many researchers in the space weather community that do monitor the space weather conditions on other planets. You may have seen photographs of aurora on Jupiter or Saturn. What's interesting is that Mars doesn't have a global magnetic field the way the Earth does. It has local magnetic fields. So when the solar wind, hits Mars, it all can hit the atmosphere and on down. And we believe that that's why Mars doesn't have much of an atmosphere left, that over the billions of years of the solar wind hitting the atmosphere of Mars, it has stripped away most of the atmosphere. And that's why it has a very thin atmosphere now, unlike the Earth, which still has a healthy atmosphere. And we appreciate that because that allows life here on the surface of Earth. And so observing, we do have lots of satellites around Mars, and they can measure the effect of the solar wind and the X-rays and so on. So we know exactly what's happening at Mars, and then we can see its effect right there. So yes, scientists at NASA and other organizations do. SANSA is perhaps going to grow in the future and may evolve into studying planetary science and space weather at other planets. Right now, the team is concentrating on space weather at Earth, but yes, space weather in the rest of the solar system is a very interesting topic.
Thank you very much, Dr. Snow. Just a comment from Dr. Pierce-Elias. Thanks very much for a very interesting and informative presentation.
Thank you.
Thank you. That was the last question. Thank you very much, Dr. Snow. The presentation and the question and answer session were really informative. Thanks for that. Thanks to our audience, for everyone who joined. This is where we end the webinar. This was part of the National Science Week as we celebrate the National Science Week with a theme evidence-based science. So thank you very much, everyone who joined us, and hope you have a great afternoon. Thank you.
All right. Thank you. Bye-bye.
Bye, everyone.